Hello and welcome everybody back to lecture video 5.3. In this video we will introduce Bayes' law and then explain how we can use it to infer the world state from the available data. And in terms of data, we actually have two sources that we would like to use to infer the world state. Namely, first we have sensor measurements that we denote with Z, and those sensor measurements can, for example, be GPS observations of our position in the 3D world. But we also have knowledge about our controls that we have sent to the motors, and those will be denoted by U. And then, of course, we need to model the relationship between these sensor measurements and our world state. And for that, we already introduced the sensor model that describes the probability between X and Z, and our motion model that describes the relationship between our previous world state, the motion command that we issued, and our new world state. And now it's important to look closely in which direction we are actually reasoning. If we go from the sensor readings to the world state, so we make observations from the sensor and try and use that to infer the world state, then this is called diagnostic reasoning. If we, however, go from the world state, if we would assume that we know the world state and we try to infer what sensor readings are likely, then this is called causal reasoning. Now, typically, at least in our situation, we are interested in diagnostic reasoning, so we would like to know where the robot is in the world, given that we make certain GPS or odometry observations. And but the problem is that diagnostic models are typically very hard to specify, and in contrast, causal models are much easier to construct, because in this way, for a causal probability distribution, you can just go from the world state and then make predictions on what the sensor is likely to report. And with Bayes' rule that we will introduce on the next slides, we can actually reverse, or we can use a causal model that's much easier to construct to actually do diagnostic inference. So Bayes' rule directly follows from the definition of conditional probability. Remember from the previous video that we can write the joint probability as the product of the conditional probability times the prior. So, for example, we can factorize the probability of x, z into the conditional probability of x given z times the probability of z. And that, of course, because we can reverse the variables, equals also the probability of z given x times the probability of x. And if we reshuffle these terms, then we directly obtain Bayes' rule. So there is no magic behind Bayes' rule, it's just the definition of conditional probability. And it says then that the probability of x, of our world state, given z, our sensor reading, can be obtained by taking the probability of z given x, which is our causal model, which is easy to compute, times the probability of x divided by the probability of z. And now let's look a little bit closer at those terms and how difficult they are to obtain. As we've said, this causal model p z given x is typically easy to construct for a given sensor. The p of x encodes the prior on the world state, so how likely is it that we are in a certain state? That's typically either known from the previous time step, or you just assume a certain prior, depending on your application. But then you have in the denominator the prior on sensor observations, and that's typically very hard to specify. This term generally says how likely it is to make a certain sensor measurement. And depending on your sensor, this might be unknown, so it's unclear how often you actually see a white pixel for a camera, or how often you make a certain distance measurement with an ultrasound sensor. That pretty much also depends on your environment around you, and so it's a bit complicated to find this term. But there is a nice trick actually to get around this. And now the idea is that we just ignore that for a second. We first compute unnormalized likelihoods that do not necessarily sum to 1. So we compute the likelihood of x given z just without the denominator. And then in a second step, we sum all likelihoods, and we know that to turn this distribution L into a proper distribution, it has to sum to 1. So we can just divide through the sum over all likelihoods in step 3 then, and this gives us the true or a proper probability distribution of x given z. And the same derivation actually for the Bayes rule that we had before also works in the presence of background knowledge. So if we now assume that we have a certain background knowledge set, then we can still do the same separation for x and y as before, and that gives us then the Bayes rule with background knowledge. So the only change here is that we always have our variables x and y conditioned additionally on a variable z, which just stays on the right side in all of the expressions. And we'll need that in a few slides. So because all of this was quite theoretic so far, I thought that we should first look at a simple example to clarify maybe a few things and to show you how Bayes' rule can be applied in practice. So imagine that we have a quadrotor that is seeking its landing zone, and let's furthermore assume that this landing zone has been marked with many bright lamps, and furthermore that the quadrotor has a brightness sensor on board to detect actually these lamps. For that it might have a special purpose brightness sensor, of course, but you can in principle also treat a camera as a very sophisticated brightness sensor just by summing over all pixel intensities. Now the problem in this example, or the reason why this is actually interesting, is that there are not only lamps above or at the landing site, but there are also some other lamps distributed around in the environment. And so the robot cannot be 100% sure that when it sees a lamp or that when the brightness sensor triggers, that it is actually above the landing site. So to formalize this problem now a little bit, assume that we have a binary sensor that gives us a reading either of that it detected brightness below it or not. And furthermore, our world state is also quite simple. We are only interested in this binary variable x, whether we are at home above the landing site or we are not. And now we can specify a sensor model where we specify the probability of detecting brightness when we are above the landing site. And for that we could, for example, determine experimentally that the brightness sensor triggers above the landing site at a probability of 60%. And by flying around at other places, we might furthermore measure that the brightness sensor also occasionally reports brightness when we are, or detects brightness when we are not above the landing site. And this value could be specified to 30%. And as you can see, if you build up a sensor model like this is now a causal sensor model, because being at home or being above the landing site causes the sensor to trigger or not to trigger. It's quite easy to construct or to measure also empirically. We could just fly with the robot or hold the quadrotor above the landing site and then measure how often it actually detects the brightness. Furthermore, we need to define a prior on our world state. If we don't have any preference, if we are 50-50, so to speak, whether we are above the landing zone or not, we could set this probability to 0.5. And now let's furthermore assume that the robot actually observes light, so z equals bright. And now we would like to know what the probability is, given the sensor model and our prior, that we are actually above the landing site, given that the brightness sensor has triggered. And as you can see from the simple example already, it's not straightforward to tell the result, because the sensor model goes in the wrong direction, and now we need this diagnostic reasoning to determine the value of or to determine the world state from our sensor reading. But fortunately, of course, we are aware of Bayes' rule, so we can use Bayes' rule now to reverse our causal knowledge just by filling in now the variable names in Bayes' rule. We obtain the equation in the middle, and now the only thing that is new is actually the denominator, where we already filled in the normalization constant, which in this case, which always can be computed just by summing up over all possible values of our world state. And if we then fill in the values and compare it, we find that after making this observation that there has been light, that light was detected below the quadrotor, then the probability of being above the landing spot now increases from 0.5 to 0.67, which is considerably higher, but it is still not, might not be confident enough to actually trigger a landing behavior. Good. So now let's suppose that our robot obtains another observation just to verify or to consolidate its hypothesis that it might be above the landing spot. And this second observation could now come from the same sensor, just taken a few seconds later, or it could come from a completely different sensor. And then the question is, how can we integrate this new information in our probability estimate or in our estimate of the world state? So more generally, how can we actually estimate the probability in which world state we are, given that we made a sequence of observations Z1 to Zn with our sensors? And for that, we can now use a Bayes formula with background knowledge that we've seen in the previous video. Remember that when we want to apply Bayes' rule in a setting where we have background knowledge, then we can just keep this background knowledge always on the right side of the bar. So when we apply this Bayes rule now with background knowledge, we obtain this relatively large term in the upper right. And now let's first look at the data likelihood that we would now have to evaluate. So this says that we need the likelihood of making a sensor observation Zn given the world state and the values of all other sensors. And this probability or this likelihood might not be easy to construct, because for that we would have to know how all the individual sensors interact with each other and how they interact with the world state, and that's not easy to specify. But we can make a reasonable assumption here, which is the so-called Markov assumption. And the Markov assumption says that the sensor measurement at time step n is independent of all previous sensor measurements as long as we know the world state x. So it doesn't matter at all what all the other sensors measure. As long as we know what the world state is, we can make a prediction using the sensor model what our sensor will tell us. And this now simplifies a little bit the expression from above. You can now see that we can strip off this whole dependency on Z1 to Zn minus 1 by applying the Markov assumption. But still these other two terms still remain and give us a hard time. But then we remember that we can apply this trick with the law of total probability in the denominator. So instead of computing this prior probability of a certain sensor reading, we can just replace it by a normalization constant and then say that we postpone this normalization until the end because we know that this probability distribution over the world state, our posterior probability distribution over the world state, has to sum to 1 at the end because it needs to be a proper probability distribution. And now we still have one complicated term here on the right side, the probability of x, given the sensor measurements of Z1 to Zn minus 1. And, but now it becomes apparent that this is actually the same as with what we started in the beginning, just that we have already removed now the first sensor observation Zn, or the latest sensor observation Zn. So we could just apply again this principle Bayes rule recursively, and this gives us then a very neat expression, as you see in the last line. So when we apply n times Bayes' rule, then we obtain n normalization constants, but in principle that doesn't matter to us because we anyway normalize then at the very end. And then we take the product over all the individual sensor models for the ith sensor, and at the end, only at the very end, we need to multiply with our prior probability of what we thought that in which world state we are in the first place. Good. So now let's apply this to our toy example here. Again, the Quadrotor seeks for the landing zone. It has detected the bright lamps below it, but now let's assume that it has a second sensor with which it can actually detect a visual marker that, like this letter H, for example, below the Quadrotor, which gives a very strong indication whether or not we are at the landing site. And for this marker, again, we can specify a causal sensor model. So we can, for example, say that this sensor gives us a detection in 80% of the cases when we are above the landing site, and it also gives us false positives at a rate of 10% if we are not above the landing site. And remember from our previous example, we computed a likelihood or a probability of 67% that we think that we are above the landing site, given that we have observed the lights. So now let's assume that the robot does not observe the visual marker below it, and so we get a second observation in Z2 that equals not marker. And now the question is, what is the probability of being home now that we have obtained the second sensor measurement? And now we can either apply this recursive Bayes rule from the last slide, or we can just apply Bayes rule once more and reuse the values that we've already computed. So by doing that, we now obtain, and filling in the values, we obtain a probability of 31% after we have not observed this visual marker. And you can see that the second observation outweighs the first observation by a lot, which mostly comes from the fact that this sensor model is much more, or the sensor is much more specific, which is reflected in the probabilities stored in the sensor model. And now the second part, as we said in the beginning, or the second source of information that we have are our actions and controls that we give to the motors. And those actions, of course, also lead to changes in the world state. Just because, for example, if we fly forward, then obviously the position of the Quadrotor changes, and the position is most likely part of our world state that we try to model. But of course, other parts of the world state might also change that are not under our control. For example, other agents or other Quadrotors might move as well. There might be humans or other things that are going on that have influence on the world state. And even if we don't have other agents in the world state might change over time because it has an intrinsic dynamics, for example. Yeah. And now, in any case, the question is, how can we incorporate the actions, and in particular those actions that we are aware of, so to speak, our own actions that we have sent to the motors. So the typical actions that a Quadrotor does is obviously to change the speed of its motors, which leads to a change in pitch and roll and thrust and so on. But it's also important to note that even then the world state and in particular the position of the Quadrotor changes when the Quadrotor does seemingly nothing, just because the Quadrotor is essentially always in motion, and so it will always drift and shake even if you seem to do nothing. And the other interesting observation here is that the actions are actually never carried out with absolute certainty. So even if we specify to fly 1 meter forward, we cannot be sure that we're actually ending up at a position of +1 meter. So it's important to realize that actions generally lead to an increase of the uncertainty of the state estimate, while measurements from sensors generally decrease the uncertainty because we know better and better the more sensor observations we take where we actually are. Good. So as we said before, to model the relationship between the world state and the actions, we need a motion model or an action model. And this can be specified using a conditional probability density function where the new state x prime depends on our previous state x and the issued control command u. So to illustrate this here with a simple example, consider the following toy example. Imagine that we have a quadrotor and it can only execute a single action, namely to take off. And for some reason we are only interested in a very small part of the world state, namely whether the quadrotor is on the ground or in the air. And then we can model that using a so-called transition diagram as depicted here on the slide. So the nodes here correspond to the different world states. So we have two nodes, ground and air, and we have some arrows in between, and those arrows indicate the transition probabilities between these states according to a certain action. So when we are, for example, located on the ground and we execute the takeoff command, then with a probability of 90% the quadrotor will actually take off, but with a probability of 10% it will still stay on the ground. This could have various reasons. For example, it might not receive this command because the wireless connection is temporarily blocked, or the battery might be empty. But in principle you can consider all of this as being noise. And different states of the world might have a different noise behavior in this motion model. And then once the quadrotor is in the air, it will stay in the air with 99% probability. But even then, occasionally it will end up on the ground again, for example, because it runs out of battery. And now for actually estimating the world state based on the actions that we have issued, we can use the following formula. The problem again is, of course, that we want to estimate the probability of the world state given that we executed a certain command u. And we cannot read this out from this motion model directly because we don't know what the previous world state was. But as you know, always when we are uncertain about the world state, we can just integrate over all possible world states or sum over all possible world states x, and then multiply the motion model with the prior probability that with what we thought that we are in this state. And of course, this applies both to the discrete case, as in this previous example, as well as to the continuous case when we're dealing with continuous positions in 2D or 3D. So to illustrate this once more for the takeoff example, imagine that our prior belief on the robot state is that the robot is located on the ground. So P of x equals ground is 1. And then the robot executes a takeoff action once, and then we are interested in computing the probability of the robot being still on the ground after this action. And we do this by filling in values, by applying this formula from before and then filling in values. And we can confirm now algorithmically that the robot will still be on the ground with a probability of 10%. Good, so this summarizes this video. We've looked at the Bayes rule today, at the derivation of the Bayes rule, and then we've shown with various examples how we can use the Bayes rule to actually fuse data from multiple sensor observations into our state estimate, and how we can use the actions and motion commands that we have issued to update our belief of the current world state. And we will need both of that next week to introduce the Bayes filter and the Kalman filter.